Hello and welcome to Toddcast number 61. So we're marching on through chapter 19, and I think I mentioned this each time. I believe there are 4 more to go. We'll see how the last few things shake out. But this particular lecture, probably more geared towards getting you ready for biochem and any future chem courses you may take in terms of the big picture of things. So the content of this isn't as significant as the techniques, and hopefully it'll make sense as we go. But a very common reaction in biology, common reaction in organic chemistry, is the hydrolysis reaction. As the word implies, lysis, you're breaking something, and hydro means you're using water to do it, meaning you have some existing bond, you break that bond, and one of the atoms gets an OH, one of the atoms gets an H, meaning you also break water. So water is broken and is whatever other bond you're interested in. Now, the thing about this type of reaction is, if you have a double bond and then it goes hydrolysis, it isn't hydrolysis, it's called hydration because it's hydrolysis of the pi bond, but the molecule stays intact. Hydrolysis, as we're going to learn it, you have to actually break a sigma bond or break into 2 separate entities. So it could be you break both a sigma and a pi. So we'll see this as we go through it. But mechanistically, excuse me, it's going to follow your standard protonate, break, make, deprotonate under acidic conditions, deprotonate, make, break, protonate if it's under basic conditions. But more important than that is just recognizing the general reaction. And so I'm going to introduce something called the magic water line. And what the heck, I'm a chemist and we like to add our names to things, so I'll call it the Todd's magic water line. It's going to work as follows. So if I have this compound, notice an ester, and I want to hydrolyze it, break a bond, I'm going to put this other lone pair that's missing right here. But I want to go ahead and break this into 2 pieces. I have to decide what is the weakest bond, or the bond that can be broken. Carbon-carbon bonds are strong, that's out. Carbon-oxygen pi bond can be broken, but if that reforms, it can kick out a leaving group. So although this is the bond you'll break in the intermediate, ultimately, from start to finish, it is this bond, this leaving group, this carbon, carbonyl carbon, to leaving group, OR, it's going to be broken. So we're going to end up cleaving this right here. And if we do it with water, then we're going to end up having that OR group and that there. And it ends up, we'll get an OH on one side. And you know what? I need to rewrite this as an OH going in this direction. And then an H here. So you end up getting OH on one side, H on the other. So you get water across this line that's drawn through the broken bond. So rather than doing it so haphazardly, I'm going to do it more computer generated. So if you use catalytic H, again, the mechanism will be protonate, break, make, deprotonate. Something we've been through a few times. And you will end up with an OH and an H added. So it ends up that the carbonyl always gets an oxygen no matter what. The leaving group gets an H no matter what. And so if it's just one bond being broken, then the O you get comes with an H, so it's an OH group, and the H is just an H. So you end up getting that line right there drawn through the bond that's broken, H on the carbonyl, H on the alcohol. So when I look at the final product, this OH is this OH, this H is that H. So you'll note that you gain water. OH and H combine to make water, so hydrolysis, you add it. I'm getting ahead of myself, but what is hydrolysis in one direction, if you go the opposite way, if you had an alcohol and a carboxylic acid and heat it and drive the water off, you can do the backwards reaction. So remove all water from the system, have a catalytic acid and heat it up, and actually push it in the dehydration direction, and you'll end up getting, rather than hydrolysis, you get dehydration reaction. You lose water and you end up making a new bond. So for now, I just want to look at this forward reaction, cleaving a bond using water, and it's known as hydrolysis. Water is broken to break another, in this case, sigma bond. So let's look at another one. Again, you have a carbonyl with a leaving group, not as good a leaving group, nitrogen, because amines are weak bases. They're not the best of leaving groups, but they still can leave. So under acidic conditions, I want to hydrolyze it and do the same thing. Now, it may not be favorable. You may have to force the reaction with some energy, but just for the short term here, I want to mention, you will cleave here. And again, when you cleave just a single bond, just one bond broken, then you have to have an OH on one side, H on the other. So we end up with an OH on the carbonyl, H on the nitrogen, and these are our products. So if we want to predict the product, just simply draw a line through the leaving group, or the bond from the carbonyl carbon to the leaving group, and OH to the carbonyl side, H to the other side, and those end up being your two products. It's pretty straightforward, it's pretty simple. Okay, so what if it's not the case? What if we have what's known as an imine, or now we have two bonds? So I'm going to break the bond to nitrogen, but that means breaking a sigma and a pi both. So here it's going to be a little bit trickier. This is the bond we're going to break. Again, carbonyl, what ultimately becomes the carbonyl carbon is this one right here. So carbon with a double bond, it's going to ultimately get the O, which means I now need two H's on the other side. So it breaks in a weird way where you get two H's on the leaving group side and O on the initial side. So let me go ahead and let my computer line show it. So because it's two bonds, you get one of them, one of the atoms, in this case carbon, getting an O. The leaving group, in this case the nitrogen, ends up getting two H's. So again, my magic water line, O in the carbonyl, two H's here. So you end up with this carbonyl, which ends up being acetone, and this methylamine. So your O goes here, your two H's end up here. So fairly straightforward. Actually, it's a pretty, I don't want to say easy thing to do, but as you see a few of them, they become better and better. So let's try another one. This one, weird at first, but if you remember, this is a ketone, and a ketone is nothing more than a ketone. The magic water line in this case is going to actually go across two leaving groups. And again, because I'm breaking two bonds instead of one, I have to have an O on one side and H's on the other. So I get an H and an H, so two H's on one side line, O on the other. So when I add catalytic acid in the presence of water, then you will get that line right there. So you end up with an alcohol, and a carbonyl, once again, this acetone. So one O here, and then because of this two H's. Okay, one last one to do. So when I break a single bond, I get an OH and an H. OH goes to the carbonyl side. When I break a double bond, I'm breaking two bonds total, so I get an O and two H's. H's go on the leaving group, O goes on the carbon, H on the leaving group, O on the carbon. Finally, this one, this is going to be the trickiest of all because I now am breaking three bonds. Really, it's not that tricky. Three bonds are nothing more than two bonds plus one bond. Meaning, when I break it, I'm going to get an O and two H's and an OH and an H, which means overall, I should get an O and an OH on one side, and then three H's on the other. So I'm going to add it across there. Three bonds, so an H and an OH, and an H and two more H's for three H's total. So if I draw my line here, then you get a carbonyl, an OH, and an HHH. So again, let me do this with computer. Goes there, and you end up with the carbonyl, an OH on one side. So that OH right there, this O right here, and then 1, 2, 3 H's. 1, 2, 3 H's, although it's NH4 plus because it's acidic conditions. When it's neutralized and we isolate it, it'll be NH3. So this is a so-called magic water line. If it passes through one bond that gets broken, we got an OH to the carbonyl side, H to the leaving group side. If it passes through two bonds, got two H's to the leaving group side and O on the other atom. If it passes through three bonds, then you add all three H's to the leaving group and an OH and an H to the carbonyl. This applies to so many different reactions. So just in general, hydrolysis of pretty much anything. So you'll notice this probably more in bio than you do in OChem, but fair game in either two classes. Okay, so hydrolysis of a glycosidic linkage is most similar to. Okay, so first off, we need to find out what the heck is a glycidic or glycosidic linkage. Glycosidic means it's a bond, a linkage between two monosaccharides to form a so-called disaccharide, or a whole bunch of monosaccharides combining to make a polysaccharide. But it basically is breaking the acetal linkage into an alcohol on one side and a hemiacetal on the other. So here is a galactose connected to a glucose. Now you have to memorize it for this class. but this is lactose. So I'm just going to note that this is galactose. This is glucose, and the overall structure is known as lactose. Here is my carbonyl carbon of sorts. It's in a protected state because it's in a ketal. It's actually an acetal, excuse me, because there's an H there, not an R. So I have my acetal linkage. The easiest bond to break is the one that comes from the carbonyl. So 2 bonds O. So this is the protected carbonyl. So if I break right there, because I'm breaking a single bond, H to the leaving group, OH to the carbonyl carbon. And so if I do that, let's see what I get. There's my magic water line. There's my H on this leaving group coming out this way. Here's my OH on the remaining carbon. It moves out, and there's your water, H and OH, for overall water being added across that linkage. So now we have separate galactose and glucose generated from the hydrolysis of lactose. Hopefully this seems okay. So this is, in this case, oxidation, you have change number of bonds O. Here you have the same number of O's, so nothing changed that way. So hydrolysis is not oxidation, it is not reduction. We did not convert an ester into an acid. So sugars are aldehydes or aldoses. Ketones are converted into ketal, so that's close. So ketal and acetal, ketone and aldehyde, they're similar in that sense. So I think I'm close to something going on here. And so protecting ketone would be converting ketone into some sort of ketal. In this case, it's more like unprotecting. We're breaking the ketal and turning it, or in this case, acetal. We're breaking acetal and turning into a hemiacetal. So that's more in tune with something being broken or unprotected, having a group removed. Hopefully this question makes sense. It's kind of a tough one. It's kind of a weird one, but it makes you look at the different types of reactions in the big picture. So let's apply it then to a specific group of compounds. So I briefly mentioned the concept of an imine. So an imine is kind of like a ketone or kind of like an aldehyde. It's a double bond from carbon to a more electronegative atom, except in the case of an imine, more electronegative atom is nitrogen as opposed to an oxygen that you find in a carbonyl. So you can end up making an imine from a carbonyl pretty easily. If we note, same reaction as before, I'm going to, instead of breaking down, if I remember right, I would break it down like this. 2 H's go in the leaving group and O goes here. So if I want to go backwards, if I were to add water and go in this direction, be hydrolysis. So this is the exact opposite of hydrolysis. Instead of using water to break the amine bond, I'm just taking carbonyl, and we're going to generate water by adding an imine to it. So let me clear what I have and just say in this direction then, I'm actually losing water. So let's figure out where the water came from. So had to come from an O somewhere. So there's my O. So sure enough, O is associated with the carbonyl and had to come from nitrogen's 2 H's. So nitrogen is ultimately the leaving group if I was going backwards. So it must be the nucleophile going in this direction. So there's my water. So if I get rid of it, I simply have to connect that carbon to that nitrogen. So I'm going to refer to this instead of the magic water line. So the magic water line is hydrolysis going backwards. In the forward direction, I'm going to refer to this as the magic water box. So the magic water box, draw a box around the water atoms, H, H, and O. So there's my 2 H's, there's my O. I want to get rid of them so they're gone. Move the water and just connect the atoms. So here's your double bond. So I'm just going to draw it in more, I guess, distinctly. You can have a double bond from carbon and nitrogen and a methyl coming off. So it's pretty straightforward. Okay. Now, how does this happen? Well, you can probably guess if it's under acidic conditions, there's going to be a protonate break make deprotonate going on. If you don't get it on the first try, then you're going to have another round of protonate, break, make, deprotonate. So let's see how we do it. So step 1, sure enough, protonate. So the lone pair on the O, the most basic, the only, I guess, free pair of electrons that you can donate. So it's going to pick up the H. So now we have a protonated compound. So first step, protonate. Probably should make note of that. Protonate. Second step then is going to be break as always. Okay, so here's my protonate for step number 1. There's my break, followed by make. And then you have the species over here with nitrogen on it, has to be deprotonated. So last step, deprotonate. And I think I'm done, except I'm not done. I do not have an imine. I have both a hydroxyl and an amine on the carbon, so I need to end up doing one more round of it. So we're trying to get rid of the water. That's our leaving group, so that's what I should protonate the OH to turn into water. So no, one more round of protonate, break, make, deprotonate. So here's my protonate. So start with this compound, picks up an H from the acid again. So there's my protonate. So I'm going to have a break make. So that's going to be my break. And this is going to be my make. So there's my break make. And then last but not least, my deprotonate. Because I have 2 new bonds to form, I needed 2 rounds of PBMD, protonate, break, make, deprotonate. And voila, I end up with the compound I needed. So first I get rid of one of the bonds to O, turn into a bond to N. I get rid of the second bond to O and turn it into a second bond to N. So I go from a double bond to an O to a double bond to a nitrogen. So it's actually a pretty easy conversion. It's actually going to happen reasonably often in bio because a lot of the mechanisms you're dealing with will involve dealing with an alpha carbon. And for whatever reason, amines will react a little bit cleaner than carbonyls, than aldehydes and ketones will. Okay, we have our mechanism. So I want to do a variation on the carbonyl to imine. And going to do that by, instead of adding a amine, I'm going to have a hydroxyamine. And so when I end up with this, what I'm calling it a hydroxyimine, I can refer to some, this is known as an oxime. But magic water box, 2 H's and an O. Box the atoms you're going to lose, then get rid of those atoms and play. After the water's gone, connect the atoms. So I now have an R, and a carbon, a 1N double bond to an N with an OH coming off. Okay, so hopefully this doesn't seem too terribly challenging. So as mentioned, that's an oxime. I'm going to play the same game. I'm going to take this compound, hydroxyamine, and when I add it across, this one's going to be kind of strange to figure out how the heck this happened. So we're going to once again figure out how this happened. And I realized I have a typo in this one. So I apologize. Instead of OH, it should be an NH2 on the other end. So this is the compound we want. So in NH2, NH2. So I get rid of this, and I connect the atoms, and you end up with that compound right there. So hopefully this seems okay. So here's my double bond to N, and I end up with this compound. And this is called a hydrazone. And the compound I used originally was hydrazine, but this is known as a hydrazone where it's been added for a carbonyl. Very common reaction to identify the ketone. So even if you can't get the ketone because it has a weird boiling point or some strange behavior, you can turn it into a hydrazone and then get the mouth point of the hydrazone. If you know the mouth point of whatever the hydrazone is, you know what the mouth point of the original carbonyl was. Okay, so again, I apologize for that typo there. Onward we go. Carbonyl is secondary imine. So now it's going to get a little bit trickier. So if I want to go to a secondary imine, then I'm adding, in this case, I'm going to add a nitrogen that has 2 R's on it instead of just 1. And so the problem here is, in order to make this happen, we need to have an O and 2 H's. And here we only have 1 H. So we get hung up a little bit. We'll figure out how to get around this. So protonate. got that, check. Break, got that. Make, got that. Just need a deprotonate step. So the A- conjugate base is going to come in and take off that H. So this is pretty much the same thing we had before. Everything's looking pretty much identical, with the exception of there's no second H to take off this. So let's see where we go with it. So protonate, I'll do that again. So I'm going to protonate the OH, make it a better leaving group. Once I have that, then leaving group is going to leave. So I'm going to have break, followed by make. So I'll put that in. This is going to be a break step. This is going to be a make step. So I'm going to break and make. But here's the catch. This compound right here has nothing to be deprotonated in the area of the nitrogen. So you end up deprotonating the alpha proton. We mentioned this at the start of this chapter, but on one carbon away from the carbonyl carbon. So this is the carbonyl carbon. It's now the imine carbon. If I call this the imine or the foundation of it structurally, one away here and here are known as alpha. So we're going to deprotonate a so-called alpha hydrogen, one on the carbon adjacent to the carbonyl or imine, as it were. So deprotonation is going to occur, but not in the usual spot. When it deprotonates, these electrons can now go up here, which bounces those electrons up there and gets rid of the plus charge. So you end up with, ta-da, an amine. So you end up not getting a secondary carbonyl, or I mean a secondary imine from that. You end up getting so-called enamine. So imine versus enamine, just want to bring that up. So in this case, here's my ketone to start out with. If I had a primary amine, then I have two H's to lose and an O, so I'm going to just lose that and turn it into an imine. But if I only have one H and one O, then I have to get the second H from an alpha, so I end up getting a double bond in a different place. So it's just a straight imine formation, whereas when I use a secondary amine, I end up with an enamine. So it ends up taking the alpha proton here. Could also take that one, but by symmetry, it's the same thing. So hopefully this seems okay. They all fall in the category of, can you find the water? Can you find how you've added water? If you're doing hydrolysis, can you find the water you lost if you're doing some sort of dehydration step? Or in this case, a conversion from an oxygen-rich species to a non-oxygen-rich species. Okay, so I'm feeling pretty good about this. A lot of information thrown at you, so just want to mention why we're doing it, like why we even care. The amazing reason is because it's actually a fairly useful reaction. So let's just throw this compound out here. I have a ketone, quaternary carbon, another ketone over here. So lots of ketones. And I want to start trying to generate some ring closing reactions. So we'll figure out how we can do this. So L-proline, and just want to make note, sometimes we add L is just the chirality, so it's basically S-proline. But because it has relative purity, because I've isolated, let's say, from some plant or some animal, a relatively pure isomeric nature of it, it's going to bind to one side more than the other of this compound. It's going to add what's known as a chiral auxiliary. It's going to add over here. So it's going to coordinate. So proline is a secondary amine. So it's going to coordinate on this side. It's going to create some sort of chaos, if you will, on this side. Block this side and make it more reactive here. Okay. Note that we made a so-called enamine. So again, we used a secondary amine, added to a carbonyl, and formed a enamine. This is the more reactive carbonyl because it's just flat out more available. It doesn't have this bulky group nearby. So these two stay intact. If I give one equivalent, it goes there. Okay, so now I had a base. Base is going to deprotonate somewhere. And the most natural thought would be the carboxylic acid. And so we need to figure out what the heck happened. There's some weirdness going on here. So if I can figure out where exactly my carbons still are. So this carbon right here has this OH. So something had to have attacked it. This is just, well, incredibly cool in the sense that I have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So if I number my ring from 1, 2, 3, 4, 5. I have 1, 2, 3, 4, 5. So enamine chemistry. This lone pair donate in here, causing that to attack there, which explains why we now have a 6-member ring that's formed, check, an O that became O minus and eventually protonated to become OH somewhere down the line, and the rest molecule intact, but we have lost this CO2 group. So the base, if it gets rid of this H, this can undergo what's known as decarboxylation. This negative can come in, out of the carbon, CO2 goes off, and you're off to the races. You now have a negative charge can move over to stabilize that N. And if we move electrons in, we can move them over here and eventually help close the ring. Okay, a lot going on in here. And so don't want you to know the mechanism, but do want you to recognize that we're using this, a chirally specific compound, to help get a chirally specific product. But in beyond that, what we also now have is this ring closing. So these alpha electrons, this pi bond can turn into an imine with negative on this carbon that can attack over here and close the ring. This is going to be a big part of what you're going to get into as we continue in carbonyl chemistry next semester. But OTOS in this case cleans up your mess. Notice that what we've done is we put tosyl H helps make this a better leaving group. It leaves, and you end up getting elimination in a way where you have a conjugated system. Pi bond is resonating with the double bond O, and so you end up with a stable compound. We have just made what's known as the Wieland-Meister ketone. It's going to be fairly important in a lot of synthetic pathways because many biomolecules have ring systems, massive ring systems. This is going to start helping us generate certain ring systems. So this first reactant has just one ring. We now have two. If this undergoes a Robinson annulation, which we will learn about in the future, you're going to end up being able to get additional ring systems or additional rings within that overall molecule. Okay. Hydrolysis of imines and enamines. So we talked about how to make them. Now we want to undo them. So when we make them, we have the magic water box, find the water, get rid of the H and H's and the O, and then plate connect the atoms. When we do hydrolysis, the magic water line, draw a line through here, add an O to the side that has the carbonyl, H's to the side that has a leaving group. Okay, so 2 bonds, so an O and 2 H's. So sure enough, we get an O on this carbon, 2 H's up there. So there's my shortcut for this one. Draw the line, O on the carbon for the carbonyl, 2 H's on the nitrogen for the amine leaving group. So same story here, except it is an enamine coming from a secondary amine to begin with. So an enamine. So this one's, again, a little bit trickier to see. We're going to cleave this bond. We're also going to add an H here and move some electrons around. So let's see how this works. I'm going to add just an H and an OH. So if I add an OH here, an OH on this carbon, H on the N. So I have an H on the N, so I have exactly what I wanted, the secondary amine. We're good. Here, though, I have what's known as an enol. If you recall, enols rapidly but rapidly will lose an H, undergo resonance, and have the H move over. So they rapidly tautomerize to form a ketone. Lots and lots of reaction information being thrown at you. So the last one I want to look at is I've looked at nitrogen compounds. So we looked at enamines and imines. Those become more and more important as you get further into chem. Also want to bring up sulfur, because sulfur is a common biological atom. So if I have 2 thiols, RSHs, and I add it across the meal, it's this exact same thing we just had with the ketal formation, except instead of OHs, or an ROH, I should say, instead of ROHs, we have RSHs. So instead of getting ORs on there, we get SRs on there. Very similar reaction, same story as before. So if I want to add it in there, then I have to figure out what exactly I'm going to break or what I'm going to form. So in one direction, if I'm undergoing dehydration, then it's a magic water box. If I'm undergoing hydrolysis, adding water across this, then it would be the magic water line. So magic water box in the forward direction, magic water line in the back direction. So here's my magic water box. I got an H from one of the thiols, got an H from the other thiol, got an O from my carbonyl. Magic water box. And so we end up getting those two bonds, which is in essence this compound right here. Perfect. This actually falls into place pretty nicely. One more example of it. We'll see how we do with this one. Again, I need to figure out what type of reaction it is. So in the forward direction, I'm losing water, so it can't be hydrolysis. Hydrolysis is gain of water. So it's not a magic water line, it's a magic water box. So there's my O, there's one H, and there's another H. So I have the ones that form water. Get rid of the water, play connect the atoms. So we're gonna end up getting this carbon right here, which has originally double bond to O. It's gonna have two more bonds, but one to one S, one to the other S. Magic water box, here I come. Draw the box right there. And remove the water, connect the atoms, and what do you have? Bart Simpson, but with sulfurs instead of oxygen atoms. So hopefully this is falling into place nicely. Again, just remember, if I break one bond, then I get an H on the leaving group and an OH on the carbonyl side. If I break two bonds, then I put an H on each of the leaving group sides and get an O. And if I break triple bond, the leaving group now gets three H's. For two H's gets an O, and for the other H gets an OH. Hopefully it is this simple, although it looks kind of like a bizarre game of tic-tac-toe. It is not. It is a game of hydrolysis and dehydration. So hydrolysis, the magic water line, and then in this case, magic water box is for dehydration. Hopefully this seems okay. One note of interest, let me get rid of all my stuff here. There's something called rainy nickel that when you treat one of these, well, for lack of a better word, sulfur protected, you can reduce it all the way down to a pair of H's, which means you can get an alkane. So alkanes are highly unreactive, so you may not want to do this, but you can do this. Sometimes we do want to get rid of all functional groups. So in this case, rainy nickel will be responsible for removing H's and taking away the sulfur. Okay, lots of information. This was a really, really long podcast. I'm hopeful that most of this sticks. The big thing, more than anything, is recognize when and how to use the magic water line and the magic water box. So have an absolutely positively wonderful day. And as we wind down, hopefully things are going well. I'm going to stop the recording, and you can tell we're going to start with wolfification and reduction when we get here next. But have an absolutely wonderful study time.